Good afternoon. My name is Fausto Vega, and I'm part of the RIS 2021 Summer Scholar Cohort. My mentor is Dr. Zachary Manchester, an associate professor at the Robotics Institute at CMU, and this project is towards the use of model predictive control for quad rotor flight. Quadrotors have rapidly advanced in control and design due to their interest in use in several applications. Some of these applications include disaster response, automated delivery, and agriculture. Their dynamics allow them to be controllable, which enables quadrotors to follow a reference trajectory with precision. Common control systems on a quadrotor include PID control, yet this type of control does not take into account obstacles and safety constraints of the system. Some of the safety constraints while flying a quadrotor are the torque limits in the motors, as well as the boundary from the flying zone. Therefore, the approach to this problem was to treat the control problem as an optimization problem. Our goal was to implement a linear quadratic regulator controller in a simulated quadrotor, and also develop methods of transferring the controller results on actual hardware. We also studied the use of model predictive control to use on a quadrotor. So as seen below, this equation is the LQR problem, which is a minimization problem of a cost function, where x of k represents the state. In this case, we have a 13-state system, 3 for the position, 4 for the rotation, because we're using quaternions, another 3 for the linear velocity, and the last 3 for the angular velocity. And Q and R represent the gain matrices based off the response in the system and the user preferences. And U of K is the control inputs, which in this case we have 4 based on the 4 motors. So in order for LQR to work, an accurate model of the system is needed. Therefore, the forces and the moments of the quadrotor were included in this model. And we also dealt with the transformation of the coordinate systems between the body and the inertial frame. And quaternions were used to determine the quadrotor attitude, as by using Euler angles, gimbal lock may happen, in which the quadrotor loses a degree of freedom, yet with quaternions, this is not a problem. So the linear quadratic regulator is a common method in control theory that provides feedback gains that ensure a closed loop stable system. So the A and B matrices of the system were solved by linearizing the drone dynamics about a hover position, and an attitude Jacobian was applied to the quaternion part of the state to make the system controllable. So it went from a quaternion representation to a 3-state representation that is called Rodriguez parameters. So these are the results of the LQR system. So the experiment was to initialize the drone at 222 and travel to a hover position at 001. And the initial position was also rotated by 45 degrees on all 3 axes to show the robustness of the system. But as you can see, it goes to its position in around 5 seconds. And the simulation in the next slide will demonstrate this experiment. So as seen here, the quadrotor starts at 222 and it goes to its goal position at 001 in around 5 seconds. We'll see it again. So for the communication part of the project, the hardware that we use was an NVIDIA Jetson Nano, an Arduino Uno, and a Holybro X500K. So for an accurate drone model, an inertia matrix and several coefficients needed to be found, which is dependent on the hardware. So the drone itself was modeled using SolidWorks, which provided the inertia matrix, and the coefficients were dependent on the propeller size. So the flight controller that was used on board the quadrotor was an Arduino Uno, and the companion computer that ran the controller was the NVIDIA Jetson Nano. The controller itself was written in Julia, and it provided optimal forces, which will then be converted to optimal PWM signals based on a relationship between the battery and the thrust. And it was sent to a subscriber, which is written in C++. And the purpose of the subscriber is to send these optimal PWM signals using the Boost serial library to the Arduino itself. And the Arduino commands the motors by sending PWM signals. And all this communication happened using 0MQ, which is a communication library, and the data itself is transferred using protocol buffers, so it serializes and deserializes the data for efficient data transfer. The model predictive control part of the project, so MPC is the constraint LQR. So some of the constraints that can be included are in the quadrator are the torque limits as well as the roll angles to ensure that the linearization is valid. And some of the solvers that were studied were Altro, which was developed by the Robot Exploration Laboratory, led by Dr. Manchester and PX2 student Brian Jackson. And another solver is OSQP, which models the minimization problem as a QP problem. And the results of this part of the project are still in progress. That concludes my progress in RIS, and I'd like to thank Dr. John Dolan and Ms. Rachel Burson for making this opportunity happen, as well as all the sponsors and speakers for supporting RIS. Thank you.